We are going to move on to the new topic, next chapter, chapter 6 of the course, and the book is Climate Change Impacts and Adaptation, an Earth System View. So the philosophy is still the same, that we know about climate change impacts, we know the need to adapt to some of the climate change that is unavoidable. So it's the managing the unavoidable versus avoiding the unmanageable. And again, here we take the Earth system view to see what are the impacts of the greenhouse gases, non-greenhouse gases, and other forcings like land use change by the human beings, and try to see what the feedbacks are that are essential. And the big difference is now adaptation is essentially local, even though at the global scale you want to bring down the total emissions and try to navigate the total global warming. But what does it mean in terms of actual local impacts? That's the key for adaptation. And in this chapter we'll again look at biophysical impacts and the consequent impacts on socio-economic systems. That's often what is under duress for adaptation. Modeling the impacts associated with future climate change obviously gives us lots of important information for planning and strategizing and implementing mitigation and adaptation responses. So it's also about doing things that are not always about trying to do business as usual and adjusting things to so that we can continue to do business as usual, because business as usual is associated with massive emissions, and they feed back to climate change. So these feedbacks are again very important. So this also represents a significant challenge for Earth system science in terms of process understanding, predictive understanding, scenario designs, and actual projections. Obviously, there are ways in which the uncertainties in impact modeling have to be dealt with and managed. When you think of adaptation, obviously simple examples exist where people have learned empirically to deal with let's say year-to-year variabilities or trends that happen on secular timescales of, let's say, a decade or two, or shifts in the system. For example, Indian monsoon has an onset around June 1, has a withdrawal in the third week of September. That gives you a length of the season between the onset and the withdrawal. And then there are a number of rainy days which are split into what are called active periods and break periods. Global warming is basically changing all of the things. Onset is delayed a little bit. Withdrawal appears to be earlier, squeezing the length of the rainy season. Mean rainfall appears to be decreasing over the last several decades, 5-6 decades. And active periods have become more intense, so rainfall is falling in heavier spells with widespread floods, and the duration and frequency of break periods is increasing. So some farmers have adjusted to this change to change their cropping season or crop calendar, as they call it. But the question is, how long can you do this empirical adjustment or adaptation without knowing how bad it's going to get or which way it's going to shift in the future? So adaptation and mitigation are not entirely independent. Adaptation include things like change in land use, relocation, so moving away from the coasts to deal with sea level rise, emergency and business continuity planning to deal with changes in, let's say, water stress, upgrades or hardening of buildings and infrastructure to deal with extreme events, residential programs promoting adaptation, could include energy use and even neighborhoods which are mixed use instead of commuting too much, etc. And of course health programs. Mitigation is where you're trying to a priori reduce our impact on climate change by resorting to energy conservation and efficiency, renewable energy obviously, sustainable transportation and improved fuel efficiency, capture and use of landfill and digester gas, and have carbon capture and sequestration, as well as enhancing carbon sinks in the ocean, land, etc., and even in agricultural lands. Okay. Intersecting the two, adaptation and mitigation, are things like sealing buildings, which helps deal with energy use, but also cooling and heating, green infrastructure, water conservation and energy conservation, and ideas of smart growth. Okay, the concept developed under IPCC adopted from research ideas is to think of impacts as risk, which are of course a function of hazards like floods or droughts, for example, or sea level rise; vulnerability, which is the function of a society's or individual's ability to deal with the hazard; and exposure, which is whether you are living close to coast in a low-lying area, on the mountain with snow melts and glacier melts and so on. And we'll see how risk is defined out of those three. And climate obviously has natural variability as well as anthropogenic climate change, which is why this is so urgent, which influence all these three. So we are specifically going to focus on impacts that are not just climate impacts but socio-economic impacts as well. And there is the socio-economic processes that we want to be concerned about in terms of producing future information, reliable projections for mitigation and adaptation, which include socioeconomic pathways that we touched on briefly, with options of mitigation, adaptation, sustainability, and so on. So adaptation, mitigation actions are involved in the socioeconomic processes as well as the governance issues. Either it's the global governance issues and the local and regional governance issues which need to be considered. So they affect in turn emissions and land use change, which contribute to the anthropogenic climate change. So there is the emissions impact and there is the socio-economic activities that affect emissions indirectly, like deforestation, agricultural land conversion, urbanization, and so on. So looking at avoidable and unavoidable climate change, emissions are in CO2 equivalent, which turns out to be something we have to worry about when we think about impacts and future impacts, how to convert non-CO2 gases into CO2 equivalent. Can we just do it using radiation forcing, or do we have to worry about something else? So this one is showing impacts avoidable through mitigation. So starting here in 2016, emissions in paragram CO2 equivalent. If you continue business as usual and intensive fuel use, one of the scenarios in AR4, which was released in 2005, versus emissions cut by 4% per year from 2016, which would take you the emissions down here less than 20 petagrams CO2 equivalent. And if you look at the concentration, so we will see how conversion from emissions to concentrations and conversion to CO2 equivalent in ppm is going to be dependent on various factors. This turns out to be critical as well. So concentrations in the atmosphere similar until 2030 because of these actions, and then emissions cut by 4% per year from 2016 are going to keep us somewhere over 400, which we have already reached around 420 by 2021 now. And if you look at the temperature rise associated with this scenario in the business as usual, we're going to head into this la-la land, which is considered not very safe by many measures based on past experiences, paleo evidences, and some guesswork. Nonetheless, global temperatures will be similar until about 2040. The rise of between the business as usual scenario and this mitigation scenario, but you can see that we flatten out the temperature rise eventually if we had already started by 2016, and I'm recording this in January of 2021. So obviously these are things to worry about. Maybe just to add the IPCC AR5, the fifth assessment report scenario to it, this also looks at net CO2 emissions in gigaton CO2 per year, gigaton CO2 per year, not CO2 equivalent, going into the future. And we are familiar with these by now. RCP 2.6, the safe way of staying below 2 degrees centigrade, which would require negative emissions or serious carbon capture and sequestration. So you can see that there are many scenarios done by models, and they provide the radiative forcing and the range of temperature increase. So similarly, RCP 4.5, RCP 6, and of course business as usual scenario essentially of RCP 8.5, which is relative to 1850 to 1900 baseline, would give you warming on the outer edge at more than 5.5 degrees. Okay, here again we are talking about converting net emissions into atmospheric concentrations. To do that, there are many assumptions involved in the scenarios which matter, but also the carbon cycle models in the models provide some uncertainties. So this is not a trivial issue, as we will return to later on, that whether we worry about CO2 equivalent in terms of emissions since industrial revolution or concentrations matter, because there are also impacts that have to be considered, because the CO2 emissions are easily tracked via fossil fuel use, land use change, cement production, etc. But what remains in the atmosphere depends on where the sources and sinks are, and what technology we assume will come into the future in terms of energy, transportation, buildings, industries, carbon capture and sequestration going into the future. So there are many issues. This is a long chapter, but just be familiar with all these issues, so that when you want to deal with this, you go into details of the particular direction you will have to take, whether you are working on mitigation or adaptation, or improving the models, reducing uncertainties, improving scenarios, and so on. Okay.